Right now, a planet twice the size of Jupiter is hurtling through the void. No star, no sun, completely alone in the dark. Billions of these rogue planets are floating between the stars, and some of them might be warm enough for life. We call them rogue planets, worlds that were kicked out of their solar systems or formed alone, wandering the galaxy forever. For decades, astronomers thought these orphan worlds were rare. Then we started counting them. Current estimates suggest there could be more rogue planets in our galaxy than stars. That's over 100 billion wandering worlds. Finding them is incredibly hard. They emit almost no light, no heat signature we can easily detect. They're cosmic ghosts. So how do you find a planet that doesn't orbit a star? You use gravity itself as a telescope. When a rogue planet passes between us and a distant star, its gravity bends the starlight, creating a temporary magnifying effect. This is called gravitational microlensing. The star brightens for a few hours or days, then returns to normal. The shape of that brightness curve tells us the planet's mass, distance, and whether it has any companions. In 2011, a team using the MOA telescope in New Zealand detected the first confirmed Jupiter-mass rogue planet this way. They named it MOA 2011 BLG 262. It was 20,000 light-years away, drifting alone through the galactic bulge. Since then, NASA's Roman Space Telescope mission has been designed specifically to hunt for these wandering worlds. Roman will monitor hundreds of millions of stars simultaneously, looking for those telltale microlensing events. Scientists predict it will find thousands of rogue planets, including Earth-sized ones we've never detected before. But here's the question that keeps astronomers up at night. Where did all these planets come from? There are two main theories. First, planetary billiards. Young solar systems are chaotic, unstable environments. Giant planets migrate inward, their gravity destabilizing smaller worlds. Some planets get flung out into interstellar space. Computer simulations show that nearly every solar system ejects at least one planet during its first 100 million years. Our own solar system probably kicked out an ice giant early on. We might have started with 5 giant planets, not 4. The second theory is even stranger. Some rogue planets never belonged to a star at all. They formed alone in molecular clouds, collapsing gas and dust that wasn't dense enough to ignite as a star. These are called sub-brown dwarfs, or planetary mass objects. They blur the line between planet and failed star. In 2023, the James Webb Space Telescope found dozens of these objects in the Orion Nebula, some as small as Jupiter. They're floating freely, many with their own disks of material. Some might even be forming their own moons. Now here's where it gets really interesting. A rogue planet sounds like the coldest, deadest place imaginable, right? No sunlight, no external heat source, surface temperatures dropping to near absolute zero. Nothing could survive there. But then, in 2021, researchers ran thermal models of Earth-sized rogue planets, and they found something unexpected. A thick hydrogen atmosphere could trap residual heat from the planet's formation, keeping it warm for billions of years. The surface would be frozen solid, but underneath that ice, there could be liquid water oceans. On Earth, we have entire ecosystems thriving around hydrothermal vents in total darkness, powered by chemical energy alone. A rogue planet with a liquid water ocean and active geology could, theoretically, support microbial life. It would be life that never knew a star, evolution shaped entirely by darkness and internal heat. No photosynthesis, no day or night, no seasons, just eternal night and the slow cooling of a dying world. But there's a problem with this idea. How long can a rogue planet actually stay warm? Models suggest that without additional heat input, even a massive atmosphere can only delay freezing for about 1 billion years. That's enough time for simple life to emerge, but probably not enough for complex organisms or intelligence. unless there's another heat source we haven't considered. Enter tidal heating. If a rogue planet has a large moon, their gravitational interaction generates internal friction. This is what keeps Jupiter's moon Europa warm beneath its ice. The same process could work on a rogue planet. A rogue Earth with a large moon could maintain liquid subsurface oceans for tens of billions of years. That's longer than the current age of the universe. Plenty of time for life to not just survive, but evolve. Then there's radioactive decay. Heavy elements in a planet's core generate heat as they break down. Earth's core is still molten, 4.5 billion years after formation, thanks largely to radioactive elements like uranium and thorium. A super-Earth with high concentrations of radioactive elements could stay geologically active for extraordinary timescales. Volcanic activity on the ocean floor would create nutrient-rich environments perfect for chemosynthetic life. So we have three possible internal heat sources: primordial heat, tidal heating, and radioactive decay. A rogue planet with all three could theoretically maintain habitable conditions longer than most stars will live. But then the data showed something we didn't expect, something that changed how we think about these worlds entirely. In 2016, astronomers detected radio emissions from a rogue planet candidate called SIMJ 013-656-63+0933-473. This wasn't thermal radiation. It was a powerful magnetic field, 12 million times stronger than Jupiter's. Strong magnetic fields require a liquid metal core and active dynamo processes. This thing was geologically alive. And if it has a magnetic field that strong, it could protect any atmosphere from being stripped away by cosmic radiation. A strong magnetic field could deflect those rays, preserving the atmosphere indefinitely. This means rogue planets with active cores might be better at maintaining habitable conditions than we thought. Then came another discovery that made the picture even more complex. In 2020, simulations showed that rogue planets could capture other rogue planets, forming binary systems in deep space. Two rogue worlds orbiting each other would generate significant tidal heating, potentially enough to melt ice and create oceans. They'd be locked in an eternal dance, no star required, generating their own heat through gravity alone. And here's the really wild part. We might be able to detect life on these planets. If a rogue planet has a thick atmosphere and subsurface ocean, volcanic activity would vent gases into that atmosphere. Methane, hydrogen sulfide, oxygen, the same biosignatures we look for around stars. The Nancy Grace Roman Space Telescope could detect these gases using spectroscopy during microlensing events. For a few hours, as the planet passes in front of a background star, its atmosphere would be backlit. Starlight filtering through would carry the chemical fingerprints of whatever gases are present. If we see oxygen and methane together in high concentrations, that's a sign of biological processes. On Earth, these gases react and disappear quickly unless life continuously replenishes them. The same would be true on a rogue planet. Certain gas combinations are smoking guns for life. But there's a catch. Microlensing events are unpredictable and brief. You get one shot, maybe a few hours. Roman will need to be watching the right patch of sky at exactly the right time, with spectroscopy ready to go. The odds of catching a habitable rogue planet in the act are low, but with thousands of detections expected, it's possible. Some scientists think rogue planets might actually be better places to look for life than planets around stars. Stars are violent. They flare, they emit radiation, they eventually die. Rogue planets avoid all of that. A rogue world with internal heat could remain stable and habitable for trillions of years, far longer than Earth will. And here's something most people don't realize. Advanced civilizations on rogue planets would be nearly invisible to us. No light pollution, no heat signature against a parent star, no transits. They'd be hidden in plain sight. If intelligent life evolved on a rogue planet, they'd grow up in eternal darkness, navigation by stars alone. Their astronomy would be completely different from ours. No sun to block the view, just the naked cosmos, always. They might develop technology faster because they'd need artificial energy sources from the beginning. And if they ever wanted to leave their world, they'd already understand interstellar travel better than we do. Because for them, every journey is interstellar. There's no nearby star to visit first. So where does the science stand today? We know rogue planets exist. We know they're common. We know some of them could have the right conditions for liquid water, maybe even life. But we don't know if any of them actually do. That's what the next generation of telescopes will tell us. The Nancy Grace Roman Space Telescope launches in 2027. It will revolutionize our understanding of these worlds. The Vera Rubin Observatory will scan the entire southern sky every few nights, catching microlensing events in real time. Within the next 10 to 15 years, we'll have a census of rogue planets in our galactic neighborhood. We'll know their sizes, masses, atmospheric compositions, and whether any of them show signs of activity. If we're lucky, we might even find one close enough to send a probe to. That's not science fiction, it's being discussed. Imagine landing on a world that's never seen a sunrise, drilling through miles of ice to reach an alien ocean. Sending a submarine into those dark waters, searching for life that evolved without light. But even if we never find life on a rogue planet, studying them changes how we think about habitability. For most of history, we assumed life needs a star. Rogue planets prove that's not necessarily true. That expands the possible places life could exist, not just around stars, but in the vast spaces between them. It means the galaxy could be far more alive than we ever imagined, not just on planets orbiting stars, but everywhere. Right now, the closest rogue planet we know of is probably within a few dozen light-years of Earth. It's out there, drifting silently through the dark, maybe with a frozen ocean beneath its surface. So here's my question for you. If we discovered microbial life on a rogue planet, would that change how you see our place in the universe?